let's just put two methyl groups there. So a secondary amine, two R groups on the nitrogen in the presence of acid. We no longer see the carbon-nitrogen double bond, but this is our carbon double bond, or alkene amine. So let's think about a mechanism for this. And I already gave it away in that video from the other day. So let's take our carbonyl group, and we'll just use acetone as it is here again. Dimethylamine. So actually, this looks like we'll start off the same as we did with the imine formation. Let's have this act as the nucleophile, attack the carbonyl carbon, move those electrons up onto the nitrogen, forming a dipolar intermediate. So let's have CH3. Well, we put the proton up there. So just like what we saw with the imine, forming this dipolar intermediate. Now let's carry out the same sort of proton transfers. So let's have water, and let's take off this proton to get rid of this positive formal charge. This is the same. Now we're going to have H3O plus. Let's go ahead and protonate this oxyanion, and how about, looks like I can squeeze it in here. Okay, so now what we would like to do, just like what we did with our imine, is we'd like to turn this hydroxyl group from a bad leaving group into a good leaving group. So we'd really like to protonate that so that our lone pair of electrons on the nitrogen can kick that group out. Let's go ahead and protonate that. Let's see what happens. So the step just shows protonation. This is all the same. So now what we can do is we have our good leaving group. We're going to kick it out. I'll flip this one around, put the hydrogens over there. Positive formal charge. And we have water down here. So actually, so far, everything looks the same. The only difference now between the primary and the secondary amines is, I'll use this one up here in the upper left, is that one step short of where this says imine in the box. Remember, we got to that by deprotonating the nitrogen. We had a positive formal charge on here, and we deprotonated that. It was the iminium ion. The issue with the secondary amine is we just don't have a proton that we can remove. There's two alkyl groups, two carbon-containing groups on that nitrogen. So this is where there's a difference in terms of the mechanisms, and it's because we do not have a proton that we can remove. However, what we do have is we have several protons on these adjacent carbons. I'll just put one there, one out of the 6 in this case. We have 3 here and 3 here. So to get to our amine product, what we're going to end up doing, it looks like, is we're going to take this proton off. We're going to form a carbon-carbon double bond, and then move these electrons up onto this nitrogen to remove that formal charge. So this is the different step. So what we're doing here is we're taking this proton off, forming a carbon-carbon double bond here, and then, we're taking the electrons here, we're removing the formal charge, or we're putting electron density onto the nitrogen, which will then make that nitrogen neutral. And that gives us our enamine. So even though you get a different product, the nice thing in terms of the mechanism is if we look at the imine versus the enamine, this is the same, 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 and it's only this step that's different. Why don't we take a couple minutes here and then practice one? Okay, see, I'll slide that up like that, and then I'll slide it up more in a minute. Let's take a little bit more complicated one and see how it looks the same. Let's put this in a ring. So let's take the cyclohexanone, plus this is a classic one. Let's use a 5-membered ring, okay? So we'll treat this just with a little bit of acid, and we'll see what the enamine product is that's formed. So I'll give you a minute or two here to get a head start on that reaction, if you would, please. Okay, so hopefully everyone's moving through this, and I was writing it as hopefully you're writing it as well. Same idea. I didn't finish it yet intentionally. We're going to have our secondary amine attack the carbonyl carbon with this ketone, move these electrons up onto this oxygen. We end up with our dipolar intermediate, scribbled in here, that's for sure. And now we're going to carry out a series of proton transfers. We're here we first deprotonated the positively charged nitrogen, remove that formal charge. Protonated this negatively charged oxygen. This is this species here. We're going to turn this hydroxyl group into a good leaving group by protonating it a second time. So it's shown here. And this structure in the bottom. And now we're kicking out water with using the lone pair of electrons on the nitrogen, forming this iminium ion that we have here. Now, we do not have a proton on either side of the nitrogen that we can remove. That's why it's different for the enamine. However, I'll just choose this side. We have 2 protons on each side, that carbonyl group. So we could take this proton off, move these electrons up onto this nitrogen to form our enamine. So we're end up forming a new carbon-carbon double bond here, and put the lone pair on the nitrogen. So I think what Kyle is asking, transferring this proton here and shortening all of these steps. So in reality, or in terms of the mechanism and balancing the charges and the protons, you could actually just having this oxygen take this proton off, and you'd end up being right down here and wouldn't have to write as much. I'm showing this out in every kind of painstaking step because this is probably more of how it actually happens. Since the drawing here is our tool to describe the mechanism, in reality, as this proton is being taken off, this thing is probably getting protonated from another solvent molecule, and all these protons are being transferred around simultaneously. So that's why I'm drawing it out in each step to represent. These are all the different proton transfer steps, but it doesn't probably happen. It doesn't necessarily just happen like this stepwise. So then, as Crystal asked, does it matter which side the double bond ends up on? Yes, and this is a very good question as well. In this particular case, it doesn't, and I'm particularly here using enamines that doesn't matter which side the double bond would end up on because it would be the same in both cases. If you do have differences in what you could form, so let's say you could form something like this. Versus something like this. This is where sometimes it gets to be a little bit confusing because overall, what ends up happening is this usually is the major product. Even though it's the less substituted alkene, which should be the less stable alkene, that ends up being sometimes the major product. I don't want us to necessarily worry about those things just for our discussion here right before our exam, but you're exactly right. So it does matter if you have an asymmetrically substituted enamine, and we might come back to that next week just briefly as well. So that's a great question. For right now, we're choosing compounds here like this one, which are symmetric, going around the ring. It doesn't matter.